Imagine trying to map, say, every single light bulb in a huge city at night. But you're stuck on the ground, and the air keeps making them shimmer, blur.
Yeah, makes it tricky.
For centuries, that was basically the challenge, right? Charting the stars accurately from Earth. You shared some really interesting history on just how fuzzy that view was.
It really was.
Today, though, we're diving into this incredible story of how he decided, well, instead of looking through the atmosphere, let's get above it. Look down at it, even. The goal: to create the most precise map of the stars ever conceived.
And it wasn't just about, getting a slightly sharper picture. It was more fundamental. They'd actually hit a wall, a limit imposed by Earth itself.
Ah,
So yeah, this deep dive is all about the journey of the Hipparcos satellite, a mission that, honestly, transformed our view of the universe
how so, exactly?
by giving us incredibly accurate measurements of where stars are and, crucially, how far away they are. The material you sent over, it really shows the clever thinking behind that leap into space.
Exactly. And for you, the learner, tuning in, think of this as your fast track to understanding a really pivotal moment in exploring the cosmos. We'll break down why it was such a game changer.
Yeah, point out some of the surprising turns.
And make sure you come away feeling, genuinely informed, maybe a bit awestruck, but not like you've just sat through a lecture.
Definitely. Our main guide here is this excerpt, Hipparcos, The Push to Space. It's a really well-researched account of how this mission happened.
Right.
It digs into the scientific dead ends astronomers had hit, this really innovative idea for a way forward, and then, surprisingly, the complex web of scientific and political hurdles they had to clear.
Okay, so our mission today, let's lay it out. Understand why space was essential for accurate star mapping. Explore how the Hipparcos concept actually emerged.
All right.
And then follow its, well, challenging journey from just an idea to a funded flying mission. Okay, let's unpack it. What was that fundamental barrier for Earth-based astronomers back in the, say, latter half of the 20th century? It wasn't just bigger telescopes anymore.
That's the key thing. By then, we'd built some truly massive, impressive ground telescopes. Size, optical quality. Those weren't the main bottlenecks anymore.
Oh, yeah.
The real problem was something we just couldn't engineer our way around down here. Our own atmosphere.
Ah, the atmosphere. Great for sunsets. Terrible for pinpointing stars, apparently.
Precisely. It causes what the source calls these bending and twinkling effects.
Yeah.
Like looking at something through water.
Yeah, it wavers.
That's what Starlight was doing. Made precise measurements, especially over large angles in the sky, incredibly difficult.
Yeah.
Almost impossible, really.
Like trying to measure the exact distance between two fireflies flickering in a breeze.
That's a good way to put it. And it wasn't just the air causing problems, was it? The actual telescopes had issues too.
Right, the mechanics of them.
Exactly. The source mentions tiny variations in telescope alignment, just the daily temperature swings, day to night.
Heating up, cooling down.
Yeah, the huge structures would expand, contract just enough to throw things off.
Yeah.
And then there was variable flexing.
Flexing. The telescopes were bending.
Under their own weight. These massive instruments, as they tracked across the sky, they'd subtly bend. More unpredictable distortion. So even the best engineering couldn't make them perfectly stable platforms.
So getting a steady reading was like trying to hold a camera perfectly still when your hands keep wobbling.
Perfect analogy.
Yeah.
And then think about this. Any single telescope on Earth can only see part of the sky.
Right, depends where you are. Northern hemisphere, southern hemisphere.
Exactly. You can't see the whole thing from one spot. Even to see all the visible sky takes a whole year as Earth orbits the sun.
Ah, okay.
As you're trying to stitch together this complete map from all these partial views taken at different times.
When the stars themselves have moved slightly in the meantime.
Precisely. They have their own space motions, as the source calls it. So it's this incredibly complex puzzle, moving pieces constantly.
Achieving high accuracy across the whole sky sounds almost impossible then.
It basically was. The source compares the resulting map to like an ancient, distorted cartographic survey of the Earth. Primitive instruments.
Wow.
It says below 1 second of arc accuracy, which is tiny, like seeing a hair from a kilometer away. The measurements were just unreliable.
And that unreliability messed up everything else, like figuring out how stars move or how far away they are.
Critically. Especially distances. Measuring distance relies on detecting these minuscule apparent shifts called parallaxes as Earth orbits the sun.
Right.
Those tiny signals, the key to the cosmic distance scale, they were just buried, lost in the noise from the atmosphere and the instrument wobbles.
So they really had hit a fundamental wall. Bigger telescopes wouldn't fix it. They needed something radical.
Exactly. which sets the stage perfectly for this precocious proposal, as the text calls it.
To go to space, how did that idea first come about?
Well, the source credits French astronomer Pierre Lacroute, mid-1960s. Apparently, there were earlier whispers about observing binary stars or planets from space, but Lacroute's was the first really comprehensive vision for space astrometry, measuring positions and movements precisely.
Mid-60s. Wow, that's really early in the space age, isn't it? Sputnik was only, what, 1957?
Yeah, barely a decade later. Most space science back then was focused on Earth's magnetic field, early X-ray astronomy, stuff like that.
So this was different.
Very different. Quite a bold idea for the time. The source also mentions his colleague, Pierre Lacroute, was involved in those early thoughts too.
So this bold idea lands. What was the reaction? Immediate excitement.
Not exactly. The source says for years it was neither enthusiastically received nor widely embraced.
Really? Why not?
Outside a small circle, it probably seems super specialized, maybe not the best use of scarce space funding. And the text points out from the outside, people probably thought, surely we could just improve the ground telescopes.
Which we now know wasn't really feasible for this level of accuracy. Hindsight, eh?
Exactly. Plus, astrometry itself, the field, was having a tough time. Progress was slow, painstaking.
Not many flashy results.
Right, which meant fewer young researchers were coming into the field. It might have even looked like a discipline that was kind of running out of steam.
Okay, so that wouldn't help build support for a super expensive specialized space mission.
Definitely not. So Lacroute had this brilliant idea, but faced skepticism about whether it was doable and even whether it was necessary.
So how did the actual design, the Hipparcos concept, tackle these earthbound problems? What was the core breakthrough?
Lacroute's key insight, the source stresses, was simple but profound. A telescope in space operates above the distorting atmosphere,
Okay, that makes sense. No more blurring.
and it's free from Earth's gravity, causing that flexing and distortion we talked about. Huge advantage right there.
And the source mentions an uninterrupted view and perpetual nighttime. How does that work?
Right. In space, you can shield the telescope from the sun, basically permanent night. And with no atmosphere scattering sunlight, the sky is incredibly dark, much darker than any mountaintop observatory. Now, you still can't look right at the sun, obviously. There's a blind spot. But as the satellite orbits, and as the Earth orbits the sun, eventually the whole sky comes into view.
So unlike ground telescopes, it could get a complete seamless view over time.
Exactly, a massive leap. But the really ingenious part, the source highlights, was observing in two directions at once,
Two directions?
using a special split mirror. It combined light from two widely separated parts of the sky into one telescope focus.
Whoa, why do that?
It allowed them to create this vast network of wide-angle measurements linking stars all across the celestial sphere.
So not just staring intensely at one tiny patch, but making interconnected measurements across huge distances.
Precisely. Measuring relative angles between stars wasn't totally new. Bessel did it in the 19th century for parallax, but over small angles.
Right.
The revolution here, only possible from space, was doing it across vast stretches of the sky. This interconnected web was the key to nailing down those tiny parallaxes, and therefore distances, with unprecedented accuracy.
Like building a super precise 3D map.
That was the goal. A vastly improved census of stellar parallaxes, unlocking their physical properties, the galaxy's structure, everything.
And the name, Hipparcos High Precision Parallax Collecting Satellite, and a nod to the ancient Greek astronomer. Nice touch.
It is.
The source compares the potential accuracy jump to going from old sailing ship maps to modern GPS. That really hits home.
It does. A quantum leap.
Okay, brilliant idea, ingenious design, but still a rocky road to approval. What happened next?
Well, Lacroute first presented it internationally in 1967. Standard scientific process, get feedback.
Sure.
The French community developed it further, but internationally. There was interest, but also technical skepticism about some core ideas. It took nearly another decade, the source says, and other instrument designers getting involved to make it seem technically solid.
And Lacroute initially hoped the French space agency, CNES, would fund it.
Yes, but CNES eventually decided it was too complex, too expensive, too risky for France alone. That beam combining mirror, the two-direction thing, that was seen as a particularly big hurdle.
Okay, so if not France, then?
Europe. The European Space Research Organization, ESRO, which became ESA, the European Space Agency, pooling resources seemed the only way.
Makes sense.
And astronomer Jean Kowalewski was crucial in pushing for it as a European project. The source mentions ESA forming in '75, merging ESRO and ELDO, the launcher group. This wider collaboration brought in expertise from all over Europe, spacecraft, instruments, data analysis, hugely beneficial.
So international collaboration was key.
Absolutely. And the design kept evolving. A big symposium in '74 showed wide European interest. Then in '75, Danish astrometrist Erik Hug joined.
And he made key changes.
Yes, crucial improvements. Made the satellite bolder, more efficient, but also technically simpler, more feasible. By the late '70s, after a decade of work, Hipparcos had solid scientific backing across Europe and was ready to compete for ESA funding.
Interesting that the source says it lacked instant glamour. You'd think mapping stars precisely would be glamorous.
Maybe not like pretty pictures of nebulae, but its deep scientific value was clear to astronomers. And maybe, surprisingly, not being super flashy helped later no other space agency was proposing something similar. Europe had a unique shot at this fundamental science.
So, ready to compete, but still had to navigate ESA's precarious path to approval in 1980? Sounds like more hurdles.
Oh yeah. Getting a big mission funded by ESA is tough. Lots of prep, lobbying, navigating committees. ESA does science, but also telecoms, meteorology, Earth observations, human spaceflight. Each has advisory groups.
A complex structure.
Very. To get picked, a project needs to be scientifically compelling, technically feasible, affordable, and fit ESA's strategy. Fierce competition. Projects get studied for years and still get rejected.
So, brilliant idea isn't enough. You need to convince scientists, engineers, policymakers.
Exactly. Within the science program, there are working groups, astronomy, solar system, etc. They're external scientists giving initial reviews.
Okay.
Their advice goes to the Science Advisory Committee, or SAC. More senior, looks across all fields. Then their advice goes to the Science Program Committee, the SPC.
The top level.
Right, made of national delegations from member states. They weigh the science, tech, cost, but also politics, national interests, balancing the whole program. The source calls it an explosive mix sometimes.
Sounds like diplomacy as much as science. And Hipparcos had rivals in the late 70s.
It did. In the astronomy working group, its main competitor was EXUV, an ultraviolet telescope. Hipparcos won that round, though, 8 votes to 3. A good first step.
Okay, progress. But then it went to the SAC, facing competition from the Solar System Group's pick.
Yes, and that was Giotto, the mission to fly by Halley's Comet.
Ah, Halley's Comet. That's exciting, time-sensitive, too.
Hugely. Giotto was the Solar System Group's unanimous choice, but Halley only comes around every 76 years. To catch it in 1986 meant Giotto had to be built and launched in just 5 years. Unprecedentedly fast for ESA.
Wow. So the SAC meeting in Feb 1980, they had Hipparcos, the fundamental star map, versus Giotto, the once-in-a-lifetime comet chase. Tough choice.
Incredibly tough. Discussions were really divided, lots of lobbying. Astronomers, the French delegation pushed Hipparcos. The comet science community, the German delegation, even the ESA director of science, Trendelenburg, backed Giotto. The SAC itself initially leaned towards Giotto.
Why? Concerns about Hipparcos.
Yeah, mainly cost and whether the tech was truly ready. The source mentions physicist Harry Elliott raising doubts about complete confidence in the technology, which worried some members.
So Hipparcos looked like it might lose out.
It did. The SAC tentatively picked Giotto, with conditions. They even asked for more tech studies on Hipparcos and suggested its main telescope should be funded nationally, not by ESA's central budget.
Ooh, that's a big deal. National versus ESA funding for the main instrument. Contentious.
Very. It reopened that whole debate, and it was a potentially huge setback for Hipparcos. The committee even hinted if Hipparcos needed full ESA funding, they might pick the EXUV mission instead.
Wow, so the scientific community must have reacted strongly to that.
Like a bombshell, the source says. Astronomers flooded ESA leaders with messages, protesting the arbitrary procedure, reaffirming broad support for Hipparcos. The Hipparcos science chair, Bernacca, detailed all the research already planned based on its data.
But the comet scientists were pushing back just as hard for Giotto.
Absolutely. Equally vocal, equally passionate about the unique Halley opportunity.
So, two passionate camps. The Science Program Committee meeting in March 1980 must have been intense. They had the final say.
An incredibly difficult position. The meeting chair, a Maldi, a respected figure, faced a room reflecting deep division. Delegations regretted the rush. Germany, Sweden favored Giotto. France, Belgium, Netherlands, Italy favored Hipparcos. The UK wanted to delay. A vote then probably would have favored Hipparcos.
But it would have left a lot of people unhappy.
Exactly. Amaldi recognized that. So instead of a divisive vote, they negotiated a compromise.
What was the compromise?
Delicate. Hipparcos was reinstated as the next project, and ESA agreed to fund the telescope payload. That was crucial.
Okay.
Simultaneously, Giotto got a 3-month extension for study. If it proved feasible within a strict cost limit, it would also be included, fast-tracked. The rationale, as the official history puts it, the stars could wait while the comet could not be stopped.
The stars could wait while the comet could not. Evocative. So both got the green light, eventually. But not everyone was happy.
Not entirely. The SEC chair was reportedly unhappy, offered to resign over the cost of the Hipparcos payload, and ESA funding it a break from solar system mission norms. The final decisions came in July 1980. Still a bit uneasy, Germany agreed to drop its request for alternative Hipparcos funding. France still voted against Giotto, citing lack of U.S. participation in experiments. But Giotto was adopted, 10 votes to 1, with the clear understanding Hipparcos would follow.
A real behind-the-scenes drama. Science, politics, budgets, national interests. The source calling scientific objectivity sometimes a luxury feels quite pointed.
It highlights that these big decisions are rarely just about the science. It's a complex mix.
So despite all that, both missions launched. And were huge successes, right? Giotto's Halley flyby in '86 was massive news.
A global event, yeah. Huge technical win for ESA. But those financial concerns raised during the debate, they kind of played out.
How so?
The source notes that in the whole 1980s, despite growing ambitions and industrial capability, ESA only launched 3 major science missions: Exosat, Giotto, and Hipparcos. Way below the target of 1 per year, partly due to the cost and complexity of these flagships.
And Hipparcos itself, it came so close to not happening, its eventual approval was really pivotal for astronomy, wasn't it?
Absolutely critical. Eric Hugg believed if it had failed in 1980, space astrometry might have just faded away.
Really?
Yeah, he felt the community was weakening, rejection would kill faith in the field.
Yeah.
He doubted NASA would have picked it up either.
Sobering. We almost missed out. The source mentions meeting Lacroute in '81, the father of space astrometry, quietly satisfied. A nice detail.
It is.
Yeah.
And there's a street named after him in Dijon now. A fitting tribute to his vision and persistence.
So you see, this fundamental problem, seen clearly from Earth, led to this audacious idea, just leave Earth behind.
Escape the atmosphere.
And the journey of Hipparcos, it wasn't just tech. It was scientific vision, complex international teamwork, and navigating those tricky waters of funding and priorities.
And here's a really interesting thought. For years, astrometry itself, the key to the cosmic map, was seen by some as maybe a bit past its prime.
Right.
It took this radical step, literally leaping into space, to totally reignite its potential and give us accuracy nobody dreamed of before.
It makes you think, doesn't it? How often do really tough problems need a completely fresh look, a totally different environment? Like moving the telescope to space gave us clarity. Sometimes stepping away from the usual way of doing things is where breakthroughs happen, in any field, really.
Yeah. And consider this. What if Hipparcos had been rejected back then? How different would our picture of the Milky Way, the universe's scale, be today? Would that whole field have just dwindled?
It really makes you wonder about those crucial turning points in science. How much depends on complex decisions, politics, funding, and maybe just a bit of luck or good timing.
Definitely makes you think.
Well, if this deep dive into space astrometry's origins got you curious, maybe check out the discoveries made with the Hipparcos data, or look into Gaia, its successor mission, which is mapping even more stars now.
Building right on that legacy.
There's always more to explore, a whole universe of knowledge waiting out there.